Hey scholars, it's good to be back with you. Today I'd like to talk to you a little bit about how to find roots of equations. Now you know something about this already. We know how to find roots of a second order polynomial using the quadratic equation. The problem is that most root equations, and I would guess a large majority of them, don't have analytical roots. What's an analytical root? Well, when you can push symbols around on a piece of paper, like the quadratic equation, and find a root, that's the analytical root. Most of the time, you're going to have to find the root numerically. That is, you're going to have to do calculations on a computer to estimate the root. When I say estimate, that's an important word. Analytical roots are exact. The quadratic equation will give you an exact root. But it often includes like a square root somewhere. Maybe there's a square root of 5 or something in there. Well, that is an exact expression, but on a computer with finite precision, you can't find the square root of 5 exactly. You can only estimate it. Well, how well? Well, how well do you want? In practice, you can estimate it well enough that you don't care about the difference anymore. You can go out as many decimal places as you want. But the big idea here is when you find roots numerically, you really are estimating them. Now, it can be a very, very good estimate. And in practice, we treat them as if they're exact because the precision is so high that it doesn't matter anymore. So with all that, how do you do this numerically? Well, in previous videos, you've seen how to use the f0 and the fsolve function in MATLAB. But what are they doing inside? Well, they have some fairly sophisticated algorithms. Rather than try to dump all that on you, let's start with a very simple algorithm. We're going to use one called bisection. Now, to start, we need a function. How about that? Right? Now, there aren't many reasons, in practice anyway, that you would use a fifth order polynomial for anything. When you're looking at physical problems, second, third order polynomials are a lot more common. Having said that, I did use a ninth order polynomial one time, and I had to. It really was required by the problem. But in all the years I've been doing this, that was one time. By far, most of the time you'll see second, third order polynomials. I picked this because there is no analytical root for a fifth order polynomial. The quadratic equation exists, you've seen that. There is a cubic equation. It's a little messy, but it's not too bad. There is a quartic equation for fourth orders. It's about that long. And there is no analytical solution for anything above that. So I picked a fifth order polynomial because I know it doesn't have any analytical roots. If you're going to find a root, you have to estimate it. Right? So to start, let's go down on my computer and let's see what this looks like and find out what the roots are using MATLAB.